Hello everyone, so today we are going to be talking about chemical reactions. From this lesson, you should come away with a few things. The first is how to recognize when a chemical reaction is even taking place and the signs of a chemical reaction. You should also be able to identify the 4 different types of chemical reactions we're going to talk about today, and you should be able to predict either the reactants or the products of these chemical reactions. So just as a quick review, there are 2 types of changes: physical changes and chemical changes. A physical change is where no new substance is formed. So things like melting water, so going from ice to water, that's a change of state, but there's no new substance. Water is still water, it's just in a different state. In contrast, we have chemical changes where the particles themselves are rearranged and create different products. And these particles are reacting with another substance. So here we have iron reacting with the oxygen in the air to create iron 3 oxide, which colloquially we know as rust. So there are 2 major signs that a chemical reaction has taken place. The first is that energy is produced or absorbed in some way. And often what this actually looks like is light is produced, sound is produced, or there's a change in temperature. So either it gets hotter or it gets colder. The other sign of a chemical reaction taking place is that we can visibly see new products. And the way we can see that is if there is a color change, if there is a gas produced, if there's a solid precipitate, so that just means a solid forms. You can see that down here. We go from what is probably 2 liquids, and then we get that solid forming. Over here, we have bubbles being produced. So these are all things that you can see in the lab. So now we get into what should be new information to you. When expressing chemical reactions, so we're communicating chemical reactions with someone, we can write them as word equations or as chemical equations. So they're 2 different things. Word equations are, unsurprisingly, made up of words or the names of the chemical compounds, whereas chemical equations are made up using their formula. So you should be able to do both. Write both the word equation and the chemical equation for a chemical reaction. It's also important for you to understand the different components of an equation. And so on the left-hand side, we draw what is known as the reactants. So we put the reactants on the left-hand side. Reactants are just sort of the starting material or the substances that are going to be reacting. So what we're starting with. In that case of that rusting iron ring, our reactants would have been the iron in the ring and the oxygen in the air. So that's what we're starting with. And you can see here an example of reactants. So we have carbon dioxide and water. That would be a word equation. And we have carbon dioxide and water, chemical equation. Notice when we have more than one reactant, they are separated by a positive sign. So they're separated by a plus sign. On the right-hand side, we have products. And so products are the things that are formed from the reactants. And the products are always written on the right-hand side of the equation. These 2 sides are going to be separated by an arrow. And what this arrow says is that the reactants are going towards the products. So they are creating the products. So one thing I wanted to mention is called a catalyst. Now, chemical reactions take some amount of energy in order to occur. We would call this the activation energy. And different reactions are going to have different sort of activation energy. A catalyst is a substance that can be added to a reaction to increase the reaction rate. But the catalyst itself is never going to be used in the reaction. So it's not actually a product, it's not actually a reactant, it just kind of hangs out and helps the reaction to take place. The way that it does this is by helping to reduce the activation energy or by changing the reaction mechanism. So it means providing the reaction another pathway to take. That's about all you need to know. So when we have a catalyst as part of a reaction, it's going to go here. So what I've written down is carbonic anhydrase. It's just an example of a catalyst, and by no means do you need to remember this term. But you can see that I have placed this carbonic anhydrase, the catalyst, over the arrow, and that just tells the reader that it is neither a reactant nor a product, but it still takes part in the reaction, sort of like as an observer. So here is the crux of the lesson, the types of reactions we are going to be talking about. We are going to be talking about synthesis reactions, decomposition reactions, single displacement, sometimes also called single replacement, they're both fine, as well as double displacement, sometimes called double replacement. So I want you to pause here and think for a moment. Just in general, like the general sense of the meaning of the word, what does synthesis mean? What does synthesis as an English word mean? And I also want you to think about decomposition. What does decomposition as an English word mean? If you know what these mean, then you can predict what this type of reaction is going to be doing and what this type of reaction is going to be doing. So, a synthesis reaction is where two or more reactants combine to form one product. Now, if you pause to think about what the meaning of synthesis means, I would define it as to create, to form. And so that's exactly what we have happening here. So we have two or more reactants on the left-hand side combining to form one new product. And that's what these little squares are showing you. We've got a red circle, so that's one reactant, one chemical. We don't know what it is. And we have B, or our blue square, and that's some other chemical. And they are going to combine and form one new product. And there is going to be some sort of bond occurring between these two. So that's why they're touching. They're all nice and cozy up together. If you wanted to look at an example that you might see, we have magnesium, the symbol which is magnesium, and we have oxygen, the symbol which is O2. And when they create that new product, we will get magnesium oxide. And if we rewrote that, that would be magnesium oxide. So anytime we have two or more reactants coming together to form one product, that is going to be a synthesis reaction. Now here is as good a time as any to talk about how we write these things sometimes. So the first thing to notice is that the magnesium reactant is all by itself. When we have a metal, we are going to write it just by itself. And what I mean by just by itself is you're going to just write the symbol, nothing else. And this is in contrast to this oxygen molecule over here. So oxygen is part of what is known as Hofbrinkel. HOFBRINCL. These are known as diatomic molecules. So H as in hydrogen, O as in oxygen, F as in fluorine, Br as in bromine, I as in iodine, N as in nitrogen, Cl as in chlorine. So these are all diatomic molecules, and you may have noticed that I went and put a 2 at the bottom of all of them. And they're known as diatomic molecules because they always come in pairs. So di meaning 2, they come in 2 pairs. So whenever you see one of these Hofbrinkel in like a chemical reaction, as long as it's by itself, so we just have straight oxygen, we don't have carbon dioxide or anything, or it's not bonded to anything else, it's going to come in pairs. The way that I think of it is like these Hofbrinkel atoms don't like to be by themselves. So if they would otherwise be all alone, that's not actually what's going to happen. They're always going to have a little buddy to hang out with them. Okay, so on this slide we talked about synthesis, we talked about writing metals just by their own symbol, and we talked about some of these Hofbrinkel diatomic molecules and how they always need a buddy. So if synthesis is creating one product out of 2 reactants, decomposition is the opposite. To decompose means to break down, to break apart. And so that's exactly what we have happening here. We have one reactant, which appears to be some sort of molecule or compound, and this reactant is breaking apart into 2 or more products. And so this compound here is breaking down into a lone circle and a lone square. An example of that might be water can break down into hydrogen and oxygen. So we have water breaking down into hydrogen and oxygen. It's just taking that reactant and breaking it apart. Now, like I said earlier, we have those Hofbrinkel molecules, and they are diatomic. So once again here, we have hydrogen, which has its little buddy, and we have oxygen, which has its little buddy. And so they're paired together because they're diatomic. So far, we have talked about synthesis reactions, where something is synthesized or created. We have talked about decomposition reactions, which is kind of the opposite, where something is broken down into smaller pieces. And now we need to talk about single displacement. So what we talked about earlier was, or maybe we didn't, but displacement is literally picking up and moving. And you can see that in our colors right here. So initially we have red and blue paired together with yellow all by itself, and it's sad by itself. On the product side, we have a swapsies of partners. So now we have blue paired with yellow, where before blue was paired with red, and now we have red all alone. And so that's exactly what a single displacement or single replacement reaction is. We are replacing one of the sort of components of the molecule or compound. And if you take a look at our sample down here, we have magnesium bromide and chlorine, which then becomes magnesium chloride and bromine. So magnesium over here is then going to be bonded with the chlorine, and bromine is going to be left out by itself. So they've just done a shuffle or a swapsies. Now, what I want you to think about is take a moment and identify which of these, if they become ions, is going to be positive and which of them are going to be negative. So is magnesium going to be positive or negative? Is bromine going to be positive or negative? Is chlorine going to be positive or negative? Pause the video if you need some time to figure that out. Go look at your periodic table of ions, figure it out. And I'm going to go ahead and go through it. So magnesium is a metal, so it's going to become positive, and specifically it will be positive 2. Bromine is a nonmetal, so it's going to be negative, and specifically negative 1. Same thing with chlorine, it's going to be negative. So chlorine is over here, bromine over here, and magnesium is plus 2. What do you notice about these pairs right here? If you need to, pause the video and give it a think. Hopefully what you notice is that we always have a positive and a minus together, creating that ionic compound. And so when trying to figure out which is going to switch with which, which atom or element is going to switch with which element, you're always going to be matching up the positives and the negatives. So our negatives are going to swap with a negative. So negative swap with a negative, and positives will swap with positives if, say, for example, this was a different sample problem. The other thing that you may notice is that these two are balanced. So because magnesium is plus 2, we have 2 chlorine to balance out those charges. So if you are predicting products, that's something you're going to have to do as well. The other thing you may notice is that we have chlorine and bromine, which are paired up with their buddy because they're part of Hofbrinkel. And finally, we're going to talk about double displacement. Double displacement, as the name may indicate, is just like single displacement, except doubly so. So what you can see here is we have a double swap going on. So here we have red paired with blue and yellow paired with green. And if we go into the products, there has been a swap. Let's take a look at it from our actual example down here. So we have sodium bonded to hydroxide, but over here we have sodium bonded to chloride. So we've swapped partners. Similarly, over here we have iron bonded to chloride, and over here it's iron bonded to hydroxide. And so we've just swapped partners. Hydroxide initially was bonded with sodium, but now it's bonded with iron. Earlier, I talked about how negatives will swap with negatives, and positives will swap with positives, and that is still the case here. So take a moment and identify which of these are going to be negative or positive, and or positive. If you need to, pause the video. So I'm going to go ahead and through. Sodium is going to be positive, and hydroxide is negative, negative 1. Iron is going to be positive, and now iron could be positive, I think it's 2, I could be wrong, just doing this from memory, or it's positive 3. Now this tells us it's going to be positive 3. And chlorine is going to be negative 1. Iron is still going to be positive 3, and that hydroxide is still going to be negative 1. Chlorine is still going to be negative 1, and sodium is still going to be positive 1. And one thing you should notice is that we always have a positive with a negative, positive with negative. The other thing you should notice is they are all neutral. So this positive cancels out this negative. Neutral, check, happy. Positive 3 and negative 1, that does not check out, and so we added a 3 beside the chlorine. That checks out. Over here we have positive 3 iron, so to balance that out, we have 3 hydroxide ions, and these are positive to negative balanced. Now, I know that I said we would only talk about 4 reactions, but there's actually, well, there's a few more. One of which is a combustion reaction. So combustion reaction requires a spark, oxygen, and some sort of hydrocarbon. In this case, we have methane. And so a hydrocarbon is anything with a chain of carbons, or in this case it's the simplest one, and hydrogen. So hydro, hydrogen, carbon, carbon. And all living things are made out of hydrocarbons. So wood is a hydrocarbon, paper is a hydrocarbon, and these are things that are flammable. Some fossilized hydrocarbons are things that we would consider to be fuel. So anything that we would put under the category of fossil fuels. And when we burn things, it will create two products: water vapor and carbon dioxide. So that is it for this lesson on chemical reactions. We talked about physical versus chemical reactions, as well as how to notice that a chemical reaction is taking place in the signs of chemical change. And we talked about the 4/5 different types of chemical reactions. And again, you should be able to identify the type of reaction based on information given to you. And you should also be able to predict the products or the reactants based on information given to you. Some skills that you will need in order to be successful in this is that you should already know how to write the name and chemical formula of different compounds. If you're not sure how to do that, go watch some of my other videos on ionic compounds, multivalent metals, polyatomic metals, and make sure to practice this. Good luck!